I think one thing that it would be good to get out is the latest ideas on what dark matter actually is. So, we've heard from you all how important this stuff is. It makes up a phenomenal amount of the universe. But what are the latest ideas? What have we found out about it? And what have we ruled out? Maybe, who wants to start? Would you like to start?
Sure. Yeah, so we have some pretty good ideas of what dark matter might be. We think it's a particle. And we're looking to find out what kind of particle it might be. There's lots of different ways to do that. So it turns out one of the things that happens is that depending on what kind of dark matter particle you have, it actually impacts the structure formation that I told you about. So one of the things that we've learned about dark matter is that it has to be pretty close to something that we call cold dark matter. And cold dark matter basically means it's a particle which moves fairly slow compared to the speed of light. If it was a really fast-moving particle, then it would basically move really fast out of those density fluctuations and erase the structure, and we wouldn't see the distribution of galaxies that we see today. So we know something about it from the galaxies, but we really want to detect that particle. So people are looking for that particle underground, and people are looking for it in the sky. If that particle, there's a chance that that particle can actually annihilate with itself and create very high energy photons. And people have been looking for it at the LHC, which is this particle accelerator in Switzerland that is actually trying to create dark matter by smashing particles together at very high energies. So we haven't found it yet. But we're certainly at the cusp of, either, many of the popular ideas for what dark matter, what particle it could be, will be tested in the next 5 to 10 years. So it's a very exciting time.
So do you have a checklist? Do you have, right, this is my book on dark matter, and these are the different particles that I need to go through? Is it a process of elimination?
It kind of is a process of elimination, yeah. We might get lucky and find it soon, or, it could be that our best ideas are just not right.
And dark energy then, so we're talking about something totally different. Dark energy is, well, maybe Adam, you could say a few more words about what dark energy is and how we're going to investigate that.
Right, it's almost self-defined as that which accelerates the universe, because that's what we see directly, but it's more than that. I mean, through other kinds of measurements, the kinds that Renée talked about in particular, we see that there is that amount of energy there, because energy has other effects on the universe. It distorts the shapes of and the size of the clumps of hot and cool matter in the early universe. So we know that there is that amount of stuff there. We know it accelerates the universe. But what we're still having trouble getting our arms around is, what is the actual physical mechanism for it? And it's not surprising that we're having a hard time with this. To explain and understand dark energy really requires the combination of two areas of physics that are just really incompatible. Quantum theory, which is the physics that we use to describe the subatomic world, and general relativity, which is the physics we use to describe the macroscopic world. These two theories are not compatible. We've been looking for a long time for the quantized theory of gravity, a kind of unification of these. Some people in the community think string theory is the way to explain how nature quantizes gravity. What's so exciting about this phenomenon is it requires you to understand how those two theories work together. You start out by describing what the microscopic vacuum looks like, what its contents are, how many particles appear, what their energy states are, and then you try to use that knowledge, add up everything in there to describe how it would gravitate. Well, you were never supposed to do that. You were supposed to put down that textbook and pick up this other textbook. But somehow nature knows how to do that, and so, as I said, when we try to do it, we're 120 orders of magnitude off, and yet we still have the idea that at least the basic concepts there are relevant or related, but in terms of anything quantitative, we don't know. So we're hoping by measuring dark energy better, we really get a clue, like a peek into the back of nature's textbook on physics, how to unify these two things.
One of the things that's, we've been saying the word cosmological constant a lot, But what that means is that the density of this dark energy is constant in the universe. Now, just to bring home how weird that is, if I took this bottle and I doubled its volume, but I kept the amount of water the same, the density of particles in the bottle would decrease. Okay, if I took a box of gas and I made the box bigger, but I didn't add any more particles, the density would decrease. And that's what we see happening with normal matter. As space expands, normal matter dilutes, the density dilutes. But dark energy as a cosmological constant, because its density remains constant. So as the universe expands, if the density has to remain constant, that's not something we know how to do. And that's really why dark energy can't be a particle that we understand. It's really something that has a constant density, which means as the universe expands, there's more of it. So in the far future, dark energy will become more and more and more important. So now it's sort of 73%. As we go further and further into the future, dark energy will grow in how important it is in the universe, which is super weird.
That is blowing my mind. But I wanted to also ask a bit about the progress on observations and the progress on theory. Where do things stand at the moment? What's the area where you'd like to see the focus perhaps shifting? Is it that you need more observations, or is it that you need really more complex theories to try and enable us to get our heads around these things like dark energy?
I think we've been lucky in the last, 5 to 10 years, and we will continue to play a really interesting game of really matching theory with data. So theory, Einstein's theory of relativity is 100 years old. Theory has been doing well for a really long time, but the progress that we're making in observations and also computational resources is really skyrocketing. And so now you can push back against theory and say, actually, this model that you predict doesn't match the data. So, people often say, dark energy is required by observations of supernovae. And until a few years ago, there wasn't the same consensus, but really in the last 15 to 20 years, all the observations are showing similar things. And so I think that means we push back on theory a little bit, and theory then gives you new things to test, which is good.
Yeah, it's been an incredibly rich time in this field. I mean, we've just, since the mid-90s, we've just sort of had this explosion of data. I think we have a program mapped out for the next 10 or 15 years, which actually will really test these ideas at very high precision, both with supernovae, with the cosmic microwave background, with galaxy surveys, and those are going to get incredibly precise compared to what they are measuring now. And in fact, we're here for a meeting to discuss essentially how do we improve both our theories and our understanding of the data so that we can get to that level of precision in order to really learn everything we possibly can from those data.
And when it comes to the data, you talked about, Renée mentioned the 6 numbers that we need to know, and that you're working towards getting more and more precise values for those numbers. But Adam, could you say something a bit about maybe other data sets that you want to exploit, or other ways of more novel ways, different ways in the future of getting the information?
Sure. Well, those 6 numbers represent sort of initial conditions, and based on those, and as Risa had described, we should be able to predict everything about the universe today. So one thing that I work on is measuring exactly how fast is the universe expanding today. We should be able to predict that, just like when you fire an arrow into space. If you know exactly what angle that arrow was at, exactly what speed, you should be able to go downwind, and you got to measure the wind too, and you should be able to point to the spot where it lands. And so I'm down there at the spot, and I'm measuring that, and we're checking, much more finely. Is it exactly what we expected? Do we need a 7th number? Is there another piece of physics? I should say, when we say 6 numbers, one of those numbers, this cosmological constant, dark energy, assumes this sort of simple explanation, which is 120 orders of magnitude off. So we don't really understand that physics. It wouldn't be crazy to think, as we push this harder, another kind of phenomenon pops out, a 7th kind of term is required. There's more complexity. In fact, it's remarkable that with such simple math, we can predict so much, because the physics we don't really understand.
I think one of the things that's really exciting is that we do have all of these complementary measurements. So, I mean, Adam talked about measuring where that arrow was going to land. Renée basically talked about measuring extremely precisely how it's launched. And I talked about essentially measuring the, 10 plus billion years in between. And so, but it's incredibly awesome that we actually do have the data to sort of test all of those three phases. And that means we can test our theories at higher precision and look for deviations from this simple model.
We never had such precise measurements before to sort of map out in that kind of detail the whole arc of the story or of the arrow. And it all has to fit together or something's wrong. And there's enough, as I said, very uncertain parts to this story. But cosmology has changed dramatically in the last 20 years. I have older colleagues who used to call cosmology a field with 3.5 facts, because it was really much more philosophical. We knew, the sky was dark at night. That's an important fact. It really is, actually. The universe is expanding, and there's this hot glow. And that is all we knew, and we made up a pretty broad general story. But now with all this very specific information, we're getting, really down to the details. And, along the way, we learned tremendous, exciting things like, wow, the universe is filled with this weird dark energy, and that's just, one example. So it's a really exciting time in the field because of that.
One of the things we sort of haven't touched on yet, and we didn't address, but is super important and is becoming more and more important in the next few years, is we're not entirely sure how the first stars formed. So, we talked about the cosmic microwave background. It's very opaque, and then the universe becomes neutral, and these photons can propagate towards us. But then the universe is neutral for quite a long time. But because these clumps are slowly getting bigger and bigger and kind of contracting together, eventually they get clumpy enough so that they can start to form stars. And then those stars, everything progresses from then. But exactly how that happens, we have a lot of theories, but it's very hard to make measurements that far away. And so there are lots of experiments, both being built and planned, that will probe that time too, which is very exciting, and I think will give us quite a few surprises.
So it really sounds like the future is data. Okay, theories need to be developed, but there's going to be a huge amount of data to mine, data that will be collected by these new instruments and missions, and data that's already available. How do you go about coping with large amounts of data? I mean, is that a new challenge that you're having to cope with? What do you do? How do you get access to supercomputers, and how do you run your programs? Maybe Risa.
Yeah, I mean, we are definitely we have been struggling with data, but we're about to face a data deluge that, we've never seen before with this next generation of surveys. I think it's true that LSST, which is the next generation imaging survey, will essentially take more data per night than is in all of the existing books.
So this is the large
synoptic survey telescope. And, and then we also have to keep up with the predictions. So, these supercomputer simulations that we talked about, in order to actually test the models, we want to do those simulations for lots of possible universes and then test them against what we actually see. So that's definitely, data is definitely what I struggle with actually on a daily basis, is like, where do I find disk space? And, how do I analyze these ever larger data sets? But that's true both, interestingly, both on the theory side and on the observational side at this stage.
Yeah, as a good example, Adam was at the spot making measurements of supernovae and, gave us incredibly precise measurements that taught us all about this accelerating expansion of the universe. The current sample of supernovae that we use to make these kinds of measurements is, of order a few thousand. But LSST, this large synoptic survey telescope, will detect 100,000 candidate supernovae, so maybe they're a supernova, 100,000 per year for 10 years. So you've gone from a few thousand to 1 million in a decade. And if we don't really know how to deal with them, we're going to have to throw most of them away, which we don't want to do. We're working on it.
I used to be able to keep track of the names of all the supernovae that I had. We would cycle through the alphabet, through the A's to Z's. Then if there was more than 26, we'd cycle through the alphabet again. Now with 1 million, forget it.
Yes.
Well, I remember when I heard about the Gaia mission, which has since launched, mapping the motions and positions of a billion stars around our own. I mean, it is phenomenal, but we absolutely need science and data to progress in this way, don't we, to be able to answer the questions?
Yeah, absolutely. I mean, I think it really has been, the data has really been what's driving our progress from this sort of 3 facts to the fact that we actually now measure these parameters to better than 1% in some cases, and are actually able to really test for very slight deviations from this kind of strange and confusing model that seems to describe our universe.
Okay, well, we have sort of 25 minutes left, so I would like to open up for questions to the floor.
Hi, I was just wondering, how do you make sure that the measurements of the cosmic microwave background don't contain any discrepancies from galaxies or stars that emit light? How do you ensure that radiation is definitely from the beginning of the universe?
That's such a great question. I'm like, do I know you? No, that's a that's a wonderful question, and the answer is we don't. So we get light from everything, and so one of the things that's great is that we expect the cosmic microwave background. We measure it in different frequencies, just like you had different filters, and so we expect the cosmic microwave to look the same, depending on what frequency we look at it. But we expect the light from stars and galaxies to look very different. So for the same reason that the sunset is a different color if there's a lot of dust in the air, galaxies that have a lot of dust in them will look different in different frequencies. And so we actually use those multiple measurements to try and remove some of that cosmic light. But how good a job we do really affects how well we can measure cosmology. So great question.
Great, thank you. And then to the gentleman up here.
Another question really about the CMB. Could you just clarify so that I...
Oh, hi.
Just in terms of the opacity of the early universe and what's driving it, is it actually the charge distribution, or is it the actual density? In other words, is it just the fact that it's a plasma that's causing it to be opaque, or is it simply, as it cools down, the mean free path increases to the point where it can actually travel?
So it is the mean free path that increases. So the electrons and the radiation are interacting via Thomson scattering, and so as the universe cools down, it's really that the electrons are no longer liberated. Once they reform, or once they form with the protons, then that scattering process can no longer happen. So that the mean free path then increases, and we can really see the photons.
Are there any questions upstairs? Yes, I'm being waved at.
Hi,
I can't see you, but ask your question.
There are people up there.
Hi, I was actually intrigued by the comment about the fact that dark energy, the density remains constant. Is the same true for dark matter? And secondly, do we know what the ratios of dark matter and dark energy to other matter and other energy was at the beginning of the universe?
So one of them, as Renée described, matter in the universe, there's a certain amount of it, and as the universe gets bigger, it's diluted. And dark energy, there's a certain amount of it, and the universe gets bigger, and there's more of it then. Whenever you create space, you create more of this stuff. It's very strange. Like if we made this auditorium bigger, we could do that, and then suddenly there were more people in all those seats. And we found whenever we built a new seat, there was a person in it right away. That is pretty much what it's like. So what that means, by definition, is if you run this movie backwards in the early history of the universe, when it was very compact, the universe would have been like, 99.99% matter and, 0.1% dark energy. And now over time, that balance is switched. This bothers a lot of people because actually we live at a fairly special time. Just in the last few billion years, they went from 50-50, when the universe would have been neither decelerating nor accelerating, to dark energy now dominating. Off way in the future, it's going to be 99.999% dark energy and very little matter. So they trade off their sort of errors of dominance.
And just to answer your other question about the amount of normal matter versus dark matter, that actually does stay constant as far as we know. That ratio was basically set in the very early universe, and they both sort of expand and dilute in the same way. And that ratio is about 15 to 20% normal matter and about 85% dark matter, not including the dark energy part of the equation. So the dark matter really dominates, and that is, we actually think that we do need that dark matter in order to form galaxies and collapse structures.
There's been reference earlier to the death of the universe. Perhaps you could tell us what you mean by that.
Sure. So we talk about the heat death of the universe. So dark energy is not important at all to you. In fact, gravity is not that important to you either. As Risa was saying, one of the most important forces in you is the electrostatic force keeping your body from flying apart. And so in our galaxy now, dark energy is not super important. But as Adam was saying, as you go to the largest scales, dark energy becomes more important in sort of governing the overall expansion of the universe. Now, as time progresses, the amount of dark energy increases, so the ratio of dark energy relative to other stuff increases. What does that do? That further drives the acceleration of the universe. And so eventually, everything is going to be very far apart. Now, we only have a finite amount of elements in the universe to make stars, hydrogen and helium, and eventually the stars will burn out and we'll run out of material to make new stars. And everything will be very far apart. So the universe, as it expands, cools down. And it'll get colder and colder and colder. This cosmic microwave background that we measure now, radiation is only 3 degrees above the coldest temperature there is. And so in the future, it'll be too cold to measure. The stars will have run out. The universe will have some black holes in it. But basically, it'll just get very cold and continue to expand. The technical term we say is that it has a de Sitter expansion, basically just expanding forever, very cold and devoid of all life.
But that's only one possibility. I had described these 3 different possibilities for what dark energy is. That's if dark energy is the first option. Under the other 2 options, the universe could still recollapse. There are a number of different possibilities.
But that's not going to be good for you either. Recollapsing is not something you want to experience either.
I think we're seeing a snapshot of what the conference is being like this week. Okay, we're heading in. Who's got the microphone?
Thank you. As I understand it, the cosmological constant and some of the other initial conditions have to be extremely precise, to the order of 10 to the power, a million or 10 to the power 10,000. I don't know what the number is, but it has to be extremely precise for us to be in the universe that we are in. And as a corollary, people say, hey, either we're very special, which science doesn't like to believe, or we're in a multiverse. And it's almost borderline a philosophical question, but how do each of you think about, is that the only conclusion that you have? Or could there be, meaning that we are in a multiverse, or are there other possibilities that explain the sheer infinitesimal accuracy of the numbers that are needed to explain the universe? Thank you.
Mm-hmm. Who wants to take that? That's a good response.
Yeah, we probably will all have different answers. I don't know. I mean, some of those parameters are more finely tuned for life than others. So, I mean, we could live in a universe with a little bit less matter or a little bit more matter, and we probably, in that range of universes, could still get galaxies and stars and planets. The cosmological constant is a little bit different. If it were 120 orders of magnitude bigger than it is, it would be hard. We would have expanded so rapidly that we wouldn't have had time to form the structure that I told you about, and so then it would have been hard to form galaxies. So there are a lot of string theorists in particular who think that this idea sort of naturally leads you to the multiverse, to the idea that we didn't just have one Big Bang, but there was one Big Bang that started our universe, but there then were other parts of the universe that started their own Big Bangs and have their own set of parameters, and in some of those there are life, and in some of them they're not. So I think that's it's a possible story, it's a possible explanation for why we have the parameter that we have, that this cosmological constant that appears to be accelerating the universe. Personally, I don't think it's the only answer. I think that there's lots of other possibilities, and that's really what we're trying to find out. I think until we really see what that physical explanation is, for me, I'm not going to be convinced. We still have a long way to go, in my mind, to test the ideas that we have before I will personally be convinced that we sort of have to have more universes. But it's certainly a possibility.
So there was one aspect that we didn't really touch on at all in the cosmic history, and that's something we call inflation. So we look around the universe today, and I said, imagine if I asked all of you your favorite album and you said Thriller, besides the fact that that's the answer. I repeat, it would have been strange if you had all known what each other's answer would be, because you don't know each other. But now, the way of kind of quantifying that in the cosmic microwave background is when we measure the temperature. So we go to a patch of a certain size and we measure the temperature. And then we go to a patch very far away and we measure the temperature. And they agree to 1 part in 100,000. But they shouldn't have been able to know what the temperature of the other part of the universe was. That's like me going to Delhi and asking someone what their favorite album is and they say Thriller. They're very far apart. We have no way of communicating. And one of the ways you can get around this in the early universe is if you say, okay, much earlier, the universe was actually much smaller than we think. And if it was very small, so if Delhi was actually in London, then the chances that we could communicate are much greater. And so if I make the universe very small, and then I stretch it out very, very rapidly, I can communicate all of this information. So that theory was proposed to explain some of the things we see in the cosmic microwave background. And that's called inflation, as one of the ideas that came forward, because it really is the universe getting very, very large in a fraction of a fraction of a fraction of a fraction of a second, many fractions of a second. So that's great. And we test for what inflation might predict in this model and what the CMB tells us. But now some of the leading models of inflation today naturally predict that we live in a multiverse. So we have a great theory that we're trying to test, and one of the predictions of that theory are that we live in a multiverse. So in a sense, it's an interesting game, and I agree with you that it's somewhat philosophical to ask, well, okay, great. Imagine we do live in a multiverse. Now, how do we ask questions about how likely this universe is? And I'm actually interested in just that statistical problem, like how do I define how special I am relative to a universe that had more dark energy, and how can I think of that? And it definitely is bordering on the edge of philosophy, but in a very fun, scientific way.
Let me compare it to, so the principle that people use when they think about how the universe is set up for life is called the anthropic principle. And it makes this argument that, well, there's a lot of rolls of the dice going on, setting the properties of a universe, and if those aren't set just right, that's okay. There's just nobody born in those universes to complain about their fate. All of us who are in a universe and alive, it's because things worked out just right. So this can happen just by chance. An area where this argument is, I think, used very successfully is, why is the Earth 93 million miles from the sun? That's a great distance to be, because if you're a lot closer, you're Venus. If you're a lot further, you're Mars. And too cold, too hot. So that's great. So if your friend scientist was trying to derive from first principles the number 93 million miles, right? They're missing understanding that there are lots of planets and lots of stars. They come in all kinds of combinations of temperatures. The planets come in all kinds of separations. Once you understand that, it stands to reason that there will be planets at that location. And one of the things that's led us to predict is that there's life other places. And now we're looking for that life, okay? So this is still science to me. These are, we can measure these distributions. We can quantify the odds that there's life out there. We can go look for it. I don't know how to do this with the universe and the other universes. It's like a word level idea without the distributions. We can't see the other universes like we can see there are other stars or other planets. We don't know what those distributions are like. There's a lot of hand waving going on. And then we say maybe. And if we can't get back in touch with with experiments and predictions, then you even start to be concerned that it isn't science. So I think a number of us are sort of approaching it. I hope we find a real deep reason why things are the way they are, because this road going down would be sort of, in a way, the end of science the way we do it.
As you're speaking, I'm remembering a story that came out a few years ago, a piece of research that said the only way we might investigate other universes is by looking for a bruise left on our own universe. What do you think about that idea? We can't communicate directly, you can't get information from them, but perhaps they could have left a bruise as we were in contact many years ago.
So there are scientists that say, if we had different universes, sort of, you can imagine bubbles in a pot of water, and they're all going to form individual universes. If really early on they maybe encountered one another, you might see these two bubbles were colliding, and that would leave an imprint in the cosmic microwave background. It would leave a sort of strange feature. And there are many people that look for these. So one of the great things about being a cosmologist is we talk about 6 numbers, and we have a simple model, but every day we're testing for crazy things that don't fit into that model. And that's sort of our job, which is great. So someone will say, actually, there's a model that the universe is shaped like a torus. I'm going to look for that, which means I should see 2 things that are the same, or there are bubbles that are colliding, or maybe the speed of light is changing with time. And we as long as you can compute what you think the scientific observables are and what it will do to the things we see, you're allowed to test and look for interesting and different models. And one of the great things is can you go from a complicated model to predictions? And that's what Adam was saying that sometimes makes him uncomfortable is we do need to confront these theories with data to say, I predict the universe should look like this in my model, and then can I see if it's likely or not?
Thank you. Are there questions up in the balcony? Shout out if you've got the microphone.
What is dark energy made of?
Best question ever.
I wish I knew.
Could you become a scientist and tell me, please? No, we're trying. Yeah, we're really trying to understand it.
The best way I could describe it is when they told you in science class that there's such a thing as empty space, they lied. Because what we think dark energy is that there is no such thing as empty space, that there's the new frontier is nothing, I would say. What is going on in nothing, in an empty space? What does it really mean to say there's a vacuum, that I've removed everything I can remove? It seems that there's some stuff in space you can't remove. And that's what we think dark energy is, the stuff you can't remove from empty space.
Love that answer and that question. Thank you. Right, there's somebody with a microphone in here. Yes, if you've got the microphone, ask a question.
I was curious what role antimatter plays in the models, and can these dark matter tendrils in the universe form their own galactic constructions, such as our galaxies themselves?
Yeah, so it turns out that we think that our universe is really mostly made of matter and not made of antimatter. And we don't really understand why this is. So there's sort of a very fundamental, like way, way more matter than there is antimatter. And we know this because we don't see antimatter actually anywhere. And so at least in the universe that we observe, we see, these dark matter tendrils are only made of dark matter. It's quite a different thing than antimatter.
Yeah, and so one of the questions talking about why is the universe so special, why did we start off in the very early times with just a little bit more matter than antimatter? Because if they were completely equal, matter and antimatter would annihilate, and we'd be done. But there was just a little bit more matter, and here we are. So that's a very interesting and as yet not solved problem.
Hi. In one of the slides that Renée showed us, you were showing us distinction between the lensed and unlensed radiation. And I was wondering, this lensing is done by gravity, I understood. How do you find the unlensed image?
These are such great questions. But now I think you're planted by someone, my colleague. No, that's great. So we don't ever see the unlensed. So that was that's not data. That's I have a model for how that lensing will happen, and so I can make a map which doesn't have it and then make one which does and show you, but really all we get is the lensed. And so what we actually do is a lot of statistical operations. It's kind of like an inversion problem. We see the lensing, we think we know how gravity theoretically does the lensing, and then we try and reconstruct what was the stuff that did the lensing. And so how well we do that depends on how accurately we measure the map. But really, we can't ever see an unlensed CMB. We have to kind of reverse the lensing and see if we did a good job.
One of the exciting things that's just now sort of happening is that, the thing that's causing the lensing, the gravity that's doing that, is the structure along the line of sight. It's the galaxies and the galaxy clusters that are between the CMB and us. So what we actually are able to do, sort of just starting now, is actually map out those galaxies and look at how do they relate to the CMB lensing. So we have a new paper coming out next week from the Dark Energy Survey, which will actually make this measurement of galaxies that we've mapped out in the survey and looking at how do those relate to the CMB lensing measurements. And it's a really exciting new frontier that's going to get much more interesting and much more precise over the next decade.
And a nice demonstration of just how much you need that extra data.
That's right.
Okay, there was the microphone up there, and then we'll come over.
Given the idea of inflation, are we actually looking at our universe just from the inside of a bubble, which may be a mere small part of the totality? It seems to me it's almost possibly like trying to understand the ecology of the oceans from looking at a cup of water.
Right. Well, but we can make assumptions, and we do, that that the universe is what we call homogeneous and isotropic on large scales. So that is to say, we say that, your cup of water is a fair sample of the ocean, that every other cup of water would be like that. Now, that isn't true if you look at too fine a scale. It's like saying, everywhere on the earth is the same. Well, no, it isn't. Some places are deserts and some places are oceans. But if you take a big enough chunk where you're sure to include a fair mix of everything, then it is. And so we suspect that on the scale that we can see, which is called the horizon, because it's literally the horizon, it's the distance light can travel in the age of the universe, we have seen that the universe has long ago converged to being homogeneous and isotropic. We look at smaller scales, and we finally find the scale where that happens, and our sample, our horizon, is much, much bigger than that. So yeah, it's possible that as soon as you got outside the horizon, the universe is completely different, but that would be weird, because that would imply that there are special places, there's special setups for the universe. It almost goes against science to assume special conditions like that just to fool you.
One of the things we also use a lot in cosmology, because we have one universe that we can see, is we use a lot of statistics to ask and answer questions about the universe. And just like you haven't met everyone in the UK, but you can make some inferences about the height distribution of people in the UK, because we understand something about statistics and sampling, and we do that a lot in the universe. We say, I haven't met every galaxy, I'm never going to see all of them, but can I learn something about the overall properties of how the universe behaves, and then refine that as I get new information. As I meet the world's tallest man, I can refine that. But
Thank you. And the microphone at the back.
I had a question about the expansion of the universe, which was maybe covered, but basically from the beginning of the universe till now, all we're observing really in that timeline is just a freeze frame, a snapshot. How do we know that it's continuing to accelerate or decelerate? How do we know from that snapshot? So if we were to drop a ball from the middle of the auditorium and take an instantaneous measurement of its speed, but we didn't exist before it, how do we know what it was doing before?
Right, we actually do get to see the before part. We can't see the future part, but by looking out, we look back in time, and we see how fast the universe was expanding long ago. So I said it's a little bit like, if I take a ball and I toss it into the air, and my question might be, will a ball have escape velocity? Will it get away from the Earth? Well, I can measure, by taking a series of pictures, how much that ball is decelerating. And based on its speed and deceleration actually tells you how much the Earth weighs. I can predict whether it has escape velocity. So we know the whole past expansion history because we could see, as Renée described, all the way back to pretty close to the Big Bang. We know the whole past expansion history. Then we're trying to understand the constituents in the universe well enough that we can predict the future expansion history.
Thank you. We're going to go back up into the balcony.
Yeah, thanks. This is yet another question about dark energy and expansion. You explained earlier on how the universe, the amount of dark energy is constant, and the universe will expand, and eventually it'll die. The density of stars will be too light, too thin to carry on the processes we see now. But if the vacuum energy pervades the entire universe, how come as it expands and dark energy remains constant, how come the vacuum energy doesn't increase and prevent that heat death over time?
So the vacuum energy is what's driving the heat death. So when we talk about dark energy and vacuum energy in this context, we're meaning them as one and the same. So it really is, so the density will remain constant, but the amount of dark energy or vacuum energy will increase. And so it really is that, you can think of the dark energy as the kind of fuel for the accelerated expansion. And so the more vacuum or dark energy there is, the more that expansion is going to continue. So it is in fact creating its own end, universe.
And the heat we're talking about is actually the heat created essentially by stars and other things like that. And those do dilute because of the dark energy.
But dark energy, we can't harness it. It doesn't, it's not the kind of energy that could be in stars and refuel them or things like that. It's actually incredibly weak. We only feel it across vast distances, across galaxies. On the kinds of scales where you have stars and planets, it's completely unhelpful.
So unfortunately, it's probably not going to solve our energy problems on Earth.
Okay, I'm afraid we have time for one more question, which will go to the gentleman at the front. But do remember the speakers will be outside after the session.
Thank you. Can I just touch on the ending of the universe? To my understanding, that there would have been two completely opposing theories. But I read recently that there's a new theory, certainly a new theory to me, whereby the universe would end up by being ripped apart, the big rip, and even down to the level of quarks, they'd all be ripped apart. How much credence does this theory have as a genuine theory as opposed to the big crunch and the other one?
Well, let me just first explain the idea of that, why things would rip apart. So Renée was describing if the energy density, the energy from this cosmological constant is constant. It's not increasing or decreasing. Every time there's a new cubic centimeter formed in the universe, it has the same amount of energy. Another possibility for dark energy, if it's related to a field, is that the amount of energy in that cubic centimeter is either decreasing or increasing. We're not sure. If it were increasing and it just continued, then a crazy thing would happen, which is that eventually in every bound system, there would be more dark energy pushing things apart than binding energy holding those things together. Now that starts out on the largest scale, so clusters of galaxies, lots of thousands of galaxies all held together gravitationally, eventually would have more dark energy inside there if dark energy were increasing in strength, and they would become unbound. Then the same thing would happen at the scale of our galaxy. The stars would stop going around the center. They would no longer feel the gravitational pull as much as the push from dark energy. Then the same thing would happen in our solar system as the planets would stop going around the sun because more dark energy there. And this would continue disassociating the Earth, unbinding atoms, rip the universe apart is the idea. But we have no evidence that that's actually going on.
It might be interesting to know that none of this is going to happen anytime soon. So we don't, it's going to be a long time before we're done. Even in the big sort of the heat death, these are going to happen way in the future. Unfortunately, sort of 5 billion years from now, the sun is going to, cease. So that's what you should be worrying about.
I like that end point. We should think about the sun. And certainly we need a lot of time for you guys to carry on doing this research. I mean, I found this evening absolutely fascinating. And it really feels that we are gearing up for a new area of cosmology. So I just wanted to take Chair's prerogative and ask you one question to go down the line each. What do you think, given everything we've discussed tonight, the new things that are happening in cosmology, what do you think the next Nobel Prize in cosmology might be awarded for? I'll start with Adam first and we'll come down the line.
Oh, gosh, I don't know. I think, I could certainly name things that would. I think if somebody figures out what dark energy is, that would be the Nobel Prize.
Okay, dark energy. Renée?
I think I would like to see a Nobel Prize awarded really for putting together this particular model, sort of the standard model of cosmology. So there are people that have worked on parts, but there are a few greats that have done really putting the whole model together, and I'd like to see that. So the standard model of cosmology.
Standard model? Risa.
I'm going to go for dark matter. It's certainly not guaranteed, but we may not find it. But if the dark matter particle is detected, and if we're really able to measure its mass and how it interacts, that's a guaranteed Nobel Prize, and it would be extremely exciting.
Well, that's not bad. 3 possibilities for a Nobel Prize just from one evening's discussions. So I think you'll join me in appreciating the effort that all speakers have put in. They've come over, they've taken part in the conference that's been organised by UCL and given up an evening to come and tell us really some fascinating insights into the latest research in cosmology. And I think the thing that I will remember is the quote, "The new frontier is nothing." I should take that with me. So please, let's thank our speakers.